Welcome to Learning to See the World Through Mathematical Lenses. This course is for students of mathematics, physics, engineering, computer science, and anyone who wants to understand mathematics rather than memorize it. After more than a decade of tutoring and teaching, I've become convinced that much of mathematics is built on just a handful of remarkably powerful ideas. Once you truly understand them, hundreds of formulas compress into a much smaller set of principles. The goal of this course is to help you discover those ideas for yourself. Today's topics are on the screen and are bookmarked as YouTube chapters for your convenience. Today, we'll extend our Basin model to quadratic geometry, exploring approximation order, higher order differentials, global accumulation constants, and why polynomial families always enclose fixed fractions of their bounding boxes. Along the way, we'll catch our first glimpses of ideas that eventually led to Taylor series and the Fundamental Theorem of Calculus. I'm excited to have you join me in this class. Now let's get started. Does anybody remember how we went about finding the volume equation for the entire tub?
I need V equals L W uh wait. So now it's 1/2 WH times L.
Okay, so you're thinking like, okay, I've got at some height, H, I've got some width W, and the cross section in this direction is a triangle. So I've got half of that, bounding rectangle that would be there. And then I'm extruding it in the third dimension with length. Perfect. Was this the final form of our volume equation, or was there something else we were able to do?
Hmm. I think it's H is a function, so you have to write it in terms of
Yeah, like W and H
delta.
relate. Yep, because they lay on a line. I think I would prefer to have height as a function of W just because we've been dealing with height. So what would that be? Or I'm sorry, W is a function of height. I got it backwards. I prefer to have width as a function of height. I know there's a relationship, there's a line here that connects the two, the width and the height.
Like it's like right there, but I'm trying to remember.
There. Well, sometimes it's helpful to just distinguish points. So what could we place down for that point down here as far as coordinates?
0, 0.
Yeah, just make it the origin. And let's use the tuples here as height, the independent variable, and width. So then if you come up here, what's the ordered pair going to be?
Capital H, capital W.
Yeah, capital H, capital W. So we know that to find the slope of a linear function, and we know this is linear because it's a straight line that creates that relation between L and H. How would we find that slope?
Be
Delta
in,
H, sorry.
oh, no, go ahead.
Isn't it just little h over big W minus little w?
which one was it? Sorry, go ahead.
Capital H minus little h over big W minus little w.
Oh, sure. I see what you're saying there, right? But in this ordered pair down here, 0, 0.
Oh, yeah,
So we
yeah.
should be able to say like, oh, we're picking any 2 points. And for a linear relation, really any 2 points will give you the same slope, right? So there's our slope. And then what's the variable? The thing that's driving that increase of W.
Would it be the inverse would be W over H?
Yeah. And actually, I think we want change in W on top. And the reason why is if we then plug in capital H for the variable, what do we get for width? So we plug in capital H as our variable, and then width is just the full width, right, of the tank. So this was our relationship that connects width and height. All right, so we can plug that into our volume formula to make it a function of a single variable. So 1/2, where there used to be width, we're doing full width over full height times variable height. And then we have variable height and length out here. And at the end of the day, that gave us something that looked like this: 1/2 length times width over height. By the way, this is a constant set by the tank, right? Those are the dimensions of the tank. And then we have an h squared. All right, so from that volume function, and it's nice that we even know the 1/2, right? Luckily, geometry gives us the 1/2. We'll see a case where that's not as clear next. But we kind of had two methods for figuring out what a change in volume would be, what an expression for a change in volume would be. What were those two methods?
Geometric and algebraic.
Yeah. And honestly, I think we have a tendency to sometimes overly lean on algebraic when it comes to advanced math. And I think there's going to be some cases today where the geometric picture kind of helps us save time. So, also, I think in geometric terms. So, like when I look at an algebra expression, it's not immediately clear to me until I can express it in a geometric visual way. So that's just kind of how I tend to think. So let's start with a geometric and say, okay, delta V, we know that delta V looks like this, because if you pour a little bit of water into the tank, there is some of that water goes to filling a rectangular component, and some of that water goes to filling that triangular wedge, and that's the linear increasing part of the cross section. So we ended up calling those delta V0, as in 0 meaning the cross section isn't changing, and delta V1, as in the cross section is changing at a linear pace. How do we get a function of delta V0 and delta V1?
Delta V0 would be um, delta H times the initial width, and delta V1 would be delta H times delta W times 1/2.
Perfect, right? Because it's a triangle. We missed one thing here, and it is so tricky because my drawing is two-dimensional in that sense of what's shaded. But because we're talking about volume, what else do we need?
The length.
Exactly. It kind of feels like an extra useless dimension right now. Well, we'll tack it on. And then how would we write width initial in terms of height? Because I kind of want to relate everything of how V changes with the water level.
It'd be W over H times H initial.
Perfect. And then for the triangle one, a nice property of linear equations is that the delta is actually, so in other words, delta W also equals width times height times delta H. And you can kind of see what that is because delta W is just width final minus width initial. And the capital W over capital H, it can be factored out because this is a linear relation. And then we just end up with W over H times delta H. So over here where there's a delta H, I can replace it with a W over H times delta H. And then there's an additional delta H here, so we get a delta H squared. I'll write out that step just in case. We still have a delta H there. And so one thing that's kind of neat to notice here is like the total size of the tank is factored into both the rectangular bit and the triangular bit, right? That full length times full width over full height is in both of them. So that's kind of a geometric way you would go about it. Then the algebraic way, how would we do that if we know the volume function?
Do 1/2 length times width over h times h initial squared minus 1/2 length times width over height times h. Or sorry, I got it backwards. H final first and H initial last.
I do that a lot myself, so I understand. All right, H initial squared. So that's really just algebraically we're using the volume function, finding the initial value, finding the final value, and the difference between the two. Now you remember we kind of dealt with this issue of, H final squared minus H initial squared is not equal to delta H squared. It's equal to delta parentheses H squared. So how do we factor that to get ourselves a delta H? Because we need to relate change in volume to change in height. And right now we don't have a change in height. We have H final and H initial.
You could factor
We
out
could-
a. Oh, sorry.
I was going to say it's a difference of two squares.
Yes. And so what will that factor into?
It'd just be H final plus H initial times H final minus H initial,
Perfect.
and then the 1/2 LW over H.
So then we just end up with our delta H coming out of this difference of two squares thing. Now, remember last week we were really focusing heavily on valid approximation, right? Like, yes, approximate. And sometimes in school we just approximate because we're trying to match an answer, right? You see something in a physics class and it's like, prove that this looks like this. And you're like, that's kind of small. Let's get rid of it. And then it lines up. But I think sometimes we miss the part where we justify the approximation, right? So in this case, we know through geometry that the rectangular bit varies with delta H linearly. So if you increase delta H, that rectangular chunk just gets bigger in volume at a linear rate. Whereas the triangular bit, that gets bigger with delta H squared. So if you're doing a large change for delta H, like, let's say we go from, I don't know, here to here. We'll go all the way to the top. Now our delta H is pretty dang big. Trying to make it a little thicker there. So that delta H leads to a massive triangular wedge, right? That triangular wedge is huge. We definitely cannot neglect that if delta H is large. As a matter of fact, delta H squared or the triangular scaling will outperform delta H eventually. And it'll outperform it in an extraordinary way, right? Like you could even imagine if your initial spot was down here, the rectangular bit might only look like that big, and the triangular bit may look that big. So for large changes in delta H, we cannot ignore that triangle. But we talked last week, and I showed a Desmos graph, but I think most of you are very confident with what quadratics versus linears look like. But what they look like is with a linear, it doesn't matter how much you zoom in on that function, it's going to look identical, right? If you zoom in, if your range used to be 0 to 1, 0 to 1 in x and y, and you go to 0 to 0.1, 0 to 0.1, the line is going to look exactly the same. The only thing that will change are the gradations on your scales. Okay? That's linear. Quadratic, very much different, right? If this is the interval between, say, 0 and 1, if you decrease your window size to, say, here, so you change your scale in y and x accordingly, x squared looks nothing like it did when we had the larger range. And it gets extraordinarily close to 0. As you zoom in, you don't even need to zoom in that far. You get down to, by the time you're down to 0.01 in the y, 0.01 in the x, it's basically hugging the x-axis. It is more or less 0, right? So what I'm really talking about here is calculus from an engineer's perspective, right? Like if I can't even tell it's not 0 looking at it, it's 0. And if it's not close to 0 enough, we just zoom in more, right? And no matter how far we zoom in, the linear always looks exactly the same, and the quadratic continues to flatten out and look like something with 0 slope that's right on the x-axis. So that was the justification for this next step. And I want to point out, do you remember that we can make this algebraic form look exactly like this geometric form? How did we do it? How do we make those two
You
things
put
look alike?
as I say in use um you want to do you want to replace H uh with or delta H with H final plus delta H squared with H. Never mind. I don't know.
You're right on the money. It's just the reverse of what you think. So you could replace delta H's here with H initial or H final minus H initial. The way I did it was I replaced H final on this side with H initial plus delta H. And when you do that and then factor everything out and get it into the different terms, they line up perfectly. It's super cool that the algebra knows how to decompose these things into rectangles and triangles. I mean, you can't take that for granted. That's pretty dang cool. But I'm not going to do that today because we've done it before. What I am going to do, though, is discuss the important part about what the algebraic form gives us. It gives us some insight, right? We talked about squeezing delta H really small. When delta H gets really small, what does this part of the algebraic difference look like?
A differential.
Not quite. That's what this part will look like. What about this part?
That approaches 1.
It does, just one?
Well, I mean 2 over 2, right? Like
And
the
they're
H of
right. Exactly, right? So H final approaches H initial. And honestly, we're squeezing what used to be a difference of 2 volumes. We're getting it so dang close together, we may as well treat it like 1 point. So we just call it H, right? For some value of H, we're squeezing H initial, H final so close together. And like Jonathan said, when you do that, you end up with h plus h over 2 times the constant set by the size and shape of the tank. And this is super nifty. It's really nice that those h's add to 2 and cancel with the 2. Because what you're left with is length times width over height, one factor of variable h times delta h. What does this represent geometrically?
That the volume times the rate of growth of the volume.
Which volume? We've got a couple different ones going. We got the full volume change, the constant cross section change, and the triangle wedge. Which volume does this represent?
That's a tiny little piece of the isn't that just
Take a look
Oh,
over
that's
here,
the
Brendan.
triangle. Sorry.
This one looks like the triangle.
The
Wouldn't
delta
it be
V
the whole thing?
zero.
Yeah, it looks like the rectangle, right? It's got the same order of h, same order of delta h, same coefficients up front, right? So what we've found is as we squeeze delta h smaller, what pops out the other side is just the rectangular component of volume increase, or the constant cross-section contribution to the change in volume, to delta V total, right? So that's really neat because what it's telling us is over small enough intervals, actually at an instant, when you take h initial, h final, and squeeze them together into one point, essentially, the triangle does not matter anymore as long as you squeeze it small enough. And it pops right in with the rectangular form we found geometrically over here. So how convenient is it that these two terms added to 2h and canceled out with the 2 to give us back the rectangle, right? Had this had a 2 up front, it wouldn't align with the rectangle. It would be 2 of the rectangles, right? So there's something about that factoring, the difference of squares, that firstly got us a delta H because we needed a delta H to compare delta V to, but it also gave us these terms that as we squeeze them together, they cancel nicely with the accumulation factor of 1/2 for a triangular tank and give us back only the constant cross-section area. But like I said, this really only works if delta H is very, very small. If you are doing a delta H that's not very, very small, you need to do this, right? This is gospel truth for any size delta H or delta V, yeah, and delta H. And this is only for small delta H. And because we've made delta H so stinking small, we decide to use a different notation, right? Because deltas require 2 data points. These things we're calling differentials only require 1. So we start saying when we squeeze these things small, we're going to start using dV instead of delta V. I always think of it as a lowercase delta. The lowercase delta looks like a D. And then H times delta H. So that was the first difference. This is the first difference because we're just detecting change in and of itself, right? And then this we call the first differential form. And if you divide the dH over, which one of Nick's questions was, are differentials ratios, right? Can you treat them like ratios? A lot of teachers don't like it when you divide over dH. But my argument is we could have divided over dH before we shrunk it. So I think if we can divide over dH or delta H when it's a finite difference, you should absolutely be able to divide over dH when it's a really, really small difference. So, oh, and I wrote the dH one too many times. This is what we call the first derivative, and it's related to the first difference in the sense that when you squeeze the first difference low enough, get that delta H tiny, you get the first derivative. And it simply tells you how volume changes as you change height at an instant, at one point. And in this case, it's only dependent on what height you're at. Because this is a case where the cross section is increasing linearly, right? And going back to that, this is really length, or length times width. Yeah, length times width over height times height. Width over height times height is width, right? That's this formula up here. So we really have length times width. This is what? What's length times width?
Area.
Yeah, cross-sectional area. Yep. So at any instant in time, the way the volume increases as you vary height a little bit is exactly proportional to the cross-sectional area. So that's what that first derivative is really telling us. Now, we started talking a little bit about higher order differences. So does anybody remember what that looked like? I know Kane mentioned it earlier. I really want to make sure that this is as clear as it can be before we go to the quadratic case, because it does get a little hairier. So if I were to ask you, I don't want to know the change of volume. I want to know how the change of volume changes. It's applying the difference twice. Sometimes we'll write it as delta squared V. How can I write that out using algebra, say?
You got your delta V final minus your delta V initial.
Exactly. And because it requires two deltas, it's going to make sense to actually draw another data point. So before we had two, now we're going to have three. And since we have three, like we learn in physics, when we have three, we kind of ditch the initial and final, and we just start numbering them. So I'm going to have three different heights, H1, H2, and H3. And we're trying to find the change in the change. So what we're noticing is to find the second difference, you really need three data points right next to each other. So I'm going to write that down, delta 2V, 1, 2, 3. Those are the points I'm analyzing. So which change am I subtracting from which change? Or in other words, am I subtracting this area from this area or this area from this area?
You're subtracting H1 to H2 from H2 to H3.
Exactly. So I'm going to take the change between height 2 and 3 of the volume and subtract the change between height 1 and height 2 of the volume. And that's going to tell me how my change is changing, how my change in volume is changing. And we actually already know how to calculate these because once you do it for a single delta V, you can kind of just plug in the variables necessary. So what would that look like if I plugged in to the formula I already have for delta V, say 2, 3? using this formula?
That'd be wouldn't that be delta V1?
Where at?
For 2, 3? Wouldn't it just be delta uh delta V1?
Delta V1, just the subscript of 1?
Yes.
Oh, I see what you're saying, like the triangular bit. Oh, I see. We'll get there, but I think first I want to plug in for like this whole equation here, right? So let's write it out together. I'm trying to calculate delta V from 2 to 3. So the real question is, what's my height initial if I'm going from 2 to 3?
2.
Yeah, H2. So I can plug in H2 there. Delta H is still delta H. We have designed the difference of differences to have the same delta H's because we want to compare apples to apples. We don't want to compare apples to oranges. So then, whoa, this term doesn't even depend on initial height, does it? The triangular wedge shape does not depend on your initial height, just depends on the delta, right? So we've got plus 1/2 length times width over height times delta H squared. This is our delta V from 2 to 3. Now with that, what would our delta V from 1 to 2 look like?
Does H2 just become H1?
Yeah, precisely, right? It's only that rectangular change in volume that depends on initial height for this particular tank. So that just becomes H1 because that's our initial for 1 to 2. And then this is where the magic happens, right? Because notice what happens with the triangular terms. What happens with those?
Cancellations.
Yes, cancellation, right? So what we end up with is finding out that because these triangular components of the change in volume are the same for a given delta H, that when we subtract one change from the others, those triangles stop mattering, right? So they're going to cancel out. And what we're left with is, by the way, notice that L times W over absolute H and delta H are common to both of what's left. So I can factor those out, and all I'm left with is H2 minus H1 times delta H. What's H2 minus H1?
Delta H.
Delta H.
Delta H. So now we have two delta H's multiplied together, get a delta H squared. And then actually, we don't even have higher order terms, do we? That's all we have here. So when I squeeze delta H closer and closer, so as delta H gets closer to 0, we can simply say that D2 of V equals length times width over height times DH squared. Then we can divide the DH squared over because we could have divided the delta H squared over before we limited it and turned it into a differential. And that gives us what we call the second derivative. Now, in this case, we started with 3 points, 2 differences, and we've still squeezed those 3 points into 1, right? You're still moving those 3 points together until they're almost at 1 point. So this is at an instant, how is your change in volume changing over height, right? What's really interesting here is that you'll notice that if you go back up to the difference here, which was delta 2v 1, 2, 3 equals length times width over height times delta H squared. How does that relate to our triangles? What's the difference between those two?
Isn't it? You make the wait. Sorry, ask that again. Sorry.
And don't overthink it too much. What's the difference between this formula and this formula?
It's doubled.
The factor of 2, right? So we've found that the change of change is simply 2 of the triangular wedge shapes, right? And we can see that geometrically by superimposing the first change onto the second one. So we take our first change, oops, which looks like this, and we move it up to be superimposed with the second change, and we see what's left over. And this is the space that's left over. That's the change of volume. Change of the change of volume between 1, 2, and 3. And it is exactly 2 of those triangular wedges. So we can see it geometrically, what we came to algebraically. And then, of course, the last and funnest change is going to be the change of change of change. That's applying the change operation 3 times. How many points do we need to do a third difference or find the change of change of change?
Four.
H4.
Yeah, we need an H4 up here. Okay, so you get an H4 up there and draw it in. And now what we're doing is really, we're just doing another difference. We're comparing the second change from points 2 to 3 to 4, and we're subtracting the second change of volume from points 1 to 2 to 3. Notice that this is recursive. Every new question we ask, the next level of change is simply the difference of the neighboring last 2 changes, right? So we know what these look like. What's the equation we were using for the second change? What do you think, Ramsey? I see you leaned in. You're looking for it.
Is it not just that one we just did right over
It is,
here?
right? It's this one. Yep.
Yeah.
And does the second rate of change depend on initial height?
That's not.
No. So okay, we just have absolute length times width over height times delta h squared. That's our second difference from 2 to 3 to 4, minus the exact same thing represents our change from 1 to 2 to 3. So by the time we get to the third finite difference, we get a 0. And at that point, you could write it with differentials as d3v equals 0 dh cubed. And then that gives us our third derivative. We're squeezing 4 points down to a single point now, and it's telling us, hey, you run out of change, right? The change of the change of the change, that's enough. It's not changing anymore. And you can think about it this way. If this is the shape of delta 2 of 1, 2, 3, the shape of delta 2 of 2, 3, 4 is also 2 of those triangles, which we've already established, have the same area or the same volume so long as delta H is the same. So really at that point, we're just subtracting 2 parallelograms from each other of the exact same size. So this is a reduction of order and differences that we're seeing. And it leads us perfectly into something new. So now we get even more out of our comfort zone here. Let's see here. Can I click? Is it going to let me click? All right. Let's get to the quadratic basin, right? This is really the first non-trivial case where you're like, my normal geometry is not going to cut the mustard here, right? Like this is new. Um, and luckily we've got a drawing for it already, which is good because drawing this freehand is not fun. So here's a thought, okay? Let's just take some guesses. What is V of H? Or maybe even start a little earlier than that. What's V of W and H? If you know some height and some width up to a certain point of the quadratic, what's that formula going to look like?
Isn't it H sub I or 1/2? No, sorry, it's 1 I plus delta H uh, times delta V not, or sorry, times width initial plus delta W.
By the way, I'm asking for absolute volume at this point, not change. So I'm asking if I fill up the basin to a certain height, H, how much total volume is going to be in there? I heard width initial, I think that's good, right? Width initial is going to clarify how wide the water is at the top. And probably H should be involved, right? Like absolute, or I'm not absolute height, but the water level height should probably be in there. The length is still the same, right? So we know we're probably gonna have a factor of L.
Mhm.
So dimensionally, this works out. We have a length times length times length. That's a length cubed. That's a volume. Do we think that's going to work out for us?
Would we need the equation of the curve itself to know how much is missing out of that volume?
It's
Like we could take a
probably
volume of
sure.
the triangular prism and then subtract whatever that little piece is.
I think you're definitely onto something there. We should probably figure out how width and height are related, right? But before we do that, I would just like to ask, does anybody believe that there should be some sort of a constant up here? Because remember, if you're filling it up to a certain height, there is this kind of what I would call a bounding box, and that bounding box has volume, length times width times height. And surely what's in the quadratic basin must be less than that, right? The real question is it a ratio less? You know, like with the triangle, we knew with the triangle it was 1/2, right?
Is it
Now
1/8?
it could be 1/8, right? We're not quite sure yet, but we know it's less than 1/2 because the quadratic basin is actually holding less fluid than its cousin triangular would at that same height, width, and length. So we have a feeling that there should be a constant up here, maybe, right? I'm going to write it as C2 because we're dealing with a quadratic here. I'm just going to say maybe a constant.
So when you drew out the rectangular version of it, maybe that curve is like a portion of a circle. I guess a cylinder. We could
Sure.
subtract that if we knew the overall radius of that cylinder, I guess.
Yeah, it's probably not going to be exactly cylindrical, but I do think that the cylindrical version would hold less volume than the quadratic version, and the quadratic version would hold less volume than the triangular version. So if we could do a cylindrical and a triangular, we could probably squeeze and figure out an even better guess for what a constant should be. But I think for now we can say C2 should probably be less than 1/2. I'm a very incredulous person, so I honestly am like, why should it be a constant? Right? This is a weird curve. And it scales in weird ways as we looked from zooming in on the x squared curve, right? Like why should it be a constant of the bounding, rectangular prism? I think there's a way we could show it. But for now, I think it'd be a good idea to go to what Jonathan said about finding width as a function of height so we can get our volume function single variable. So let's use a similar method as before. We start at the origin for our height and width ordered pair, and we end at the same capital H, capital W. What would a quadratic width relation look like? So what should I fill in here? It's a little bit harder than the linear one, but a very similar technique. Any guesses? Because we know when we plug in W of capital H, what do we want to get back? If I plug in my width function for absolute height, what should the width be equal to?
Max width.
Max width, right? So, and it doesn't really matter how we interpolate these 2 points as long as it's quadratic. And it turns out there is one unique one. We know there's going to be a multiplication by h squared because the width varies with height quadratically. So in other words, if I plug in h here to find the width, there's going to be some h squared involved because we see that the width is like growing quadratically compared to a linear growth of height, right? So we got to make sure things cancel out to do this curve fitting. So I would argue you should probably put capital H squared in the denominator, because then when you plug in capital H for variable h, you get capital H squared divide capital H squared. And then what do we want it to spit out again, Topher?
W.
That
Max
capital. Yeah,
W.
exactly. So this formula works. It gives us, and when we plug in capital H, we get out capital W. So that's helpful. Now we can plug that into our V, which is now just a function of H. It's going to have some constant that we don't know, times length. Our width is now replaced with max width over max height squared times H squared with an H on the outside. So distributing a little bit, we get, once again, a constant based on the max parameters of the tank. But this time, instead of an h squared like we got for the triangle, or an h like we got for the rectangular bathtub, we get an h cubed. So it seems to be like one order higher. It's always one order higher than the width, right? The width was h squared, volume is h cubed. And why did this h squared have to be there for that to work? Because, we noticed we kind of just fit it there so that it would spit out the max width when we plugged in the max height. But I want you to think dimensionally.
Because if you put in capital H for H squared on the right, then you would get you wouldn't get max H. You would actually get way more. You'd get H squared times W.
Yeah.
So
You get width times height max. Yep. Absolutely. And also from a dimensional analysis perspective, we're dealing with volume. That always has dimension of length times length times length, right? So we look here, we look at the top, we go, the constant's dimensionless. It may not even be a constant, I don't know yet. But we've got length times width times height cubed. What power is that of distance?
It's a fifth power.
Yeah, distance times distance cubed, that's distance to the fifth. And we want distance cubed, so we need to divide out by a distance squared. So that h squared in the denominator is helping us stay in the third dimension. Because I don't deal outside of that. All right. So now we have two ways of going about it, right? We got the algebraic, the geometric. This is one of those rare cases where I'm like, I don't know how to do this geometrically. I really don't. I know how to do the triangle geometrically, maybe. I definitely know how to do the rectangle, but I do not know how to do that quadratic slice. But before we even get to that, let's do it algebraically and see what pops out. All right, so we're going to take the difference, delta V, both sides. And what's that going to expand into?
It's a difference of 2 cubes.
Hey, yep. It's a good thing we don't have the cubic tank. We'd have a difference of 2 hypercubes. And then I tap out. But right, because the constants can pull out of a difference operation, because the difference operation measures change and constants don't change, so those come out. And what we're left with is h final cubed minus h initial cubed. Now, there is a really cool factoring rule for differences of different powers, right? H final to the n minus h initial to the n. There's actually a really cool formula all the way up as high order as you want to go. And it always results in one delta h coming out. It always results in an h final minus h initial and something that gets bigger and bigger. Does anybody know how to factor difference of cubes here?
So H final plus H initial parentheses. Oh no, it's minus. It's H final minus H initial.
What was that?
Is it H final plus H initial?
That was what it was for difference of squares. For difference of cubes, and honestly, this would be a good, like, I'm not going to hold your feet to the flames, but a good homework assignment might be to draw a difference of 2 cubes and figure out what it would be geometrically. What it ends up being is h final squared plus h final times h initial plus h initial squared, and then times that delta h that we need to relate the volume change with the height change. So we end up with delta V equals C2 length times width over height squared times h final squared plus h final h initial plus h initial squared times delta h. The relationship between change in height, change in volume is definitely getting more complicated, but we're going to use that squeeze idea. Okay, we're going to say as delta h approaches 0, what can we then do?
We can then make H finals and initials the same.
Yep. We can say h final approaches h initial, and we'll just call it h. Okay, so at that point, if we plug that in, then this is really neat. H final squared just becomes h squared. H final times h initial just becomes h squared. And h initial just becomes h squared. And then we have the delta h. So, assuming that it was a constant, I still don't think we've proven that. What would that constant have to be to relate to delta V0? Maybe we should count
1/3.
what it would have to be 1/3. Yep. So C2, our guess, is 1/3. Because h squared plus h squared plus h squared is 3h squared, and we want to cancel that out. Because if we go over here and now we talk geometrically, we would say delta V0 is really equal to what? Because we can do the rectangle. We're good at those.
One-third length times width over h times delta h squared.
Well, but we're just dealing with a
I
rectangle.
don't know.
So what's the area of this rectangle? Right there.
Delta h w times wi.
Yeah. And then it's got the length of L. That doesn't change. So we've got length times wi times delta h. And what do you know? We've got a formula to find w in terms of h. So we could plug that in and say length times width over h squared times h squared, h initial squared, times delta h. So delta V0, or the rectangular contribution to the change in volume, is this. It's not the true change in volume, just the rectangular part. And from what we saw last time, as you squeeze h smaller and smaller, it's only the rectangular part that really contributes meaningfully. So we wanted to make this look like this, and to do so, we needed the constant to be 1/3. Because when the constant is 1/3, and we've squeezed things down, we get dv equals L times W over h squared times h times delta h, right? So we're really just trying to match those things up. But there's a lot of dubious reasoning that I just threw in there, so we have to really sort it out. Firstly, we haven't proved why it should be a constant. Secondly, even though I proved last time that the triangular error was order delta h squared, and it didn't matter compared to the delta h linear of the rectangle, this time we have an extra little quadratic wedge, right? The error, this approximation may no longer be good. So I think first we should probably show ourselves that the error terms from these does scale much more rapidly down than the rectangular component or contribution. So to do that, what we're going to do is go back to the algebraic one. Actually, you know what? There's two ways to go about this. There's always two ways to do it. But I think it's going to be more meaningful to what we're learning if we do it by using tangent lines, because that's something that is very important to calculus that we haven't really discussed yet. So I've decided that I want my triangular wedge to be defined by the tangent line to the height to width curve. That's how I'm going to section this thing out. I got my rectangular chunk, then I've got this tangent wedge, triangular wedge, and what's ever left over, I'm going to leave that for quadratic. But honestly, yeah, even before we do that, we're just trying to prove that this error does go away. So maybe we're overkilling it there. We can get there. What if we just do an overestimation? What would be a good overestimation or error bounding thing to do here, seeing as we don't really know how to find delta V1 or delta V2?
I think I have a question
Go
really
ahead.
fast. So your dv down there, isn't the h supposed to? I don't think the dimensions are right on the dv right there.
Oh, you're right.
I
It's
think
supposed to be
h needs to be
squared.
squared.
Yep, exactly. Good catch. All right, so has anybody come up with a method for how we could prove that this error goes away when we shrink delta H enough?
We could compare like the outer bounds of it. So the one with delta V1, and then can I draw on this?
Yeah, you should be able to.
So
You can do
this
animate.
this one, like it's hard to see, but that would be the biggest it could be, right? And
So
this would be the smallest that it could be. Is that
are
what you're
you
saying is the bounds?
Oh, I see what you're saying. I think those bounds are useful, but I think we still don't know how to calculate them. So we're looking for something that we can encapsulate this piece in that we know how to calculate easily. So what might be a natural shape to
Uh,
encapsulate that in?
The triangle.
What's that?
The triangle first,
Yeah, we could do
maybe?
a triangle. It still might be kind of hard to calculate, but we could probably do a triangle. Do you want to go with a triangle or with a rectangle?
couldn't, couldn't we couldn't we also just do the trapezoid?
This
Well,
part?
yeah. Yeah, because I was thinking maybe delta V naught plus delta V one divided by delta V two limit something like that to
Yeah,
see.
that's a good point. I think the issue there is we need to know how to calculate tangent lines for that. And I was thinking maybe we could prove the error scales in our favor even without needing to do that yet. So, who's all in favor of the triangular bound, or who wants to just shoot with hand grenades and do the rectangle?
do do a triangle.
It's definitely a better fit. All right, let's do the triangle. So we're gonna bound this thing up. Use a bigger line here. You can see that because the quadratic curve, like the triangle is definitely bigger, slightly, right? Ever so slightly. So how would we calculate that triangle area?
There's definitely a 1/2, I
Yeah.
think.
So I'm gonna write here error bounding. Oops. Uh-oh. My Wacom better not poop out on me right now. Gonna be miserable if that's the case. Okay, so error bounding with the triangle, and that is gonna be a 1/2. We know this side's delta H, right? What's this side?
Uh,
It's almost like a new width or something.
like an epsilon times a delta W.
Yeah,
It's actually just a delta W
yeah.
because that's the exact amount your width has changed absolutely, right? As you go from this height to this height, width of the tank has changed that much absolutely. So it is just delta W. And we know the W formula. So I'm going to say that the air E must be less than this triangle. And then for delta W, how do we take this formula and turn it into delta H's and H's?
Expand out the delta W, maybe?
Yeah. Yep. So we could say delta H, and then delta W is just
Yeah.
width over height squared times H final squared minus H initial squared. That's not delta H squared, right? How do we factor that?
HF plus HI times HF minus HI.
Yep. There's that
Delta
difference
H.
of squares, right? What was working for the volume before is now working for the width. There's kind of a relationship in the powers there. So we get an HF plus HI and an HF minus HI. And the HF minus HI is just a delta H. So we get a delta H squared. And then we just have this HF plus HI thing over here. So the air is certainly going to be less than this. So how does the air scale in terms of delta H?
It's a quadratic term.
Yeah, right. It's still scaling quadratically at maximum, right? This isn't even the actual amount that the quadratic and triangular wedge add. This is slightly bigger than that. And yet it's still going to downscale with delta h squared compared to the signal, which is the rectangular part, that scales with delta h. So absolutely, as you squeeze delta h really small, you can bet that this error is going to go to zero way quicker than the volume is, just like the same graph we looked at before. So now through error bounding, we've shown, great, all the error that could be conceivably had from this is going to scale much smaller, much quicker. So we've proven this is a useful approximation with that. Now, before we go to any more insights, I think we still need to pay the Pied Piper and prove why it is a constant, right? Because to me, that's an assumption. So, and I like stating assumptions, and I do like answering them when I can. Can't always, but sometimes you can. All right.
Can I just back the truck up a bit?
Go ahead.
What you just did just now, you made a triangle and you're saying this is my upper boundary of my volume here.
Exactly. Yeah, it was
But
the upper
so
bound of the air. Go ahead. Was Jonathan, did you have something?
I was just gonna mention that's what I was trying to draw was that and say that we should do is the triangle there
Sure.
was it just looked like I was drawing a curve because I'm bad at drawing.
Fair enough. And you know what's really neat is you can actually bound this thing with a dang rectangle, and it's still order delta h squared. And so you can still slough it. So even with a worse upper bound for air, it still works out. But now with the constant, I think this is one of the most powerful kinds of arguments that one can use in mathematics. And what I'm going to do is I'm going to draw two quadratics. And we're going to do a little compare contrast. Okay. So for the first quadratic, I'm going to have it go from 0 to 1. And that quadratic's going to grow up to a height of 1 in that interval. For my second quadratic, I'm going to go from 0 to 100. And I'm going to let it grow up to 10,000. And our question really, when you boil it down, is really, does the area under the quadratic relate to the area of the rectangle that bounds it by a constant? So in other words, with a triangle, it was straightforward. We're like, well, of course, a triangle, half the rectangle here, half the rectangle here. Now we're asking, with a quadratic, is there just a constant that relates the area of that bounding square to the area under the curve, the area in the quadratic? So the argument is this. These quadratics clearly have different ranges, right? One of them goes from 0 to 1, and it rises in height from 0 to 1. The other one goes to 0 to 100 and rises in height from 0 to 10,000. Is it safe to say that if we can show that these sorts of quadratics relate to each other in the fact that they are both ratios of what the square is, that we can kind of just say, okay, for quadratics, that bounded area is always the same ratio of the rectangle. Okay, so we don't know what the ratio is. We've got a good guess that it's probably 1/3, but here's what really hammers it home for me, okay? I'm going to go ahead and add units now. This is 0 meters to 1 meter, and it grows to 1 meter, okay? This is 0 centimeters to 100 centimeters, and it grows to 10,000 centimeters squared. Sorry, I should have squared the centimeters and meters there. Okay. Does math know the difference between actually changing the size of something or just changing the ruler you're using?
Yeah, because, or I was gonna say they would be relatively the same approaching ratio of their sides, or something like that.
So if it was a ratio, so you're saying math knows a difference between unit conversions and actual size differences.
No.
You would say no. What do we
Well,
think? Does anybody have arguments one way or the other?
How would math know that you're talking about meters
Right.
or centimeters?
It doesn't. It just deals with the numbers, right?
Yeah.
The units are for us, so we can agree on what things are. So is it
so
safe to say that when I add units to this picture, that these quadratics are identical in reality? If I laid one on the other, they would be the exact same thing in reality.
no,
Why not?
because 1 centimeter is way different than 1 meter when you zoom in.
Agreed, but I accounted for that, right? I go from 0 to 1 meter here. I go from 0 to 100 centimeters there. There's 100 centimeters in a meter, right? So they have the same width. Now we know these are quadratic, so I have to square the input to get the output, right? I accounted for that too. 100 squared, I think, is 10,000. I always struggle with these. Um, and 1 meter squared is 1 meter squared, right? So before I added the units, these looked like different sized objects, different sized quadratics. Then when I added the units to them, it was revealed that they were actually identical. If math can't tell the difference, then those ratios have to be the same. So that's my argument for why absolutely there is a constant, and this quadratic takes up exactly 1/3 of the bounding rectangle, no matter where you measure it from. This is a lens that I like to call detectable versus undetectable change. It has a lot to do with symmetry. The idea behind it is that oftentimes when you can't detect change in a system, there's a beautiful symmetry there. So what this symmetry is trying to tell us is that if you go home and graph 100 different quadratics, you can change the range and domain on your Desmos or graphing calculator and make them look identical. There is only one quadratic. It's just the frame within you with which you zoom into it that changes. But there's only one shape that's a quadratic, and it always takes up 1/3 of the bounding rectangle. Those of you that integrate a lot, you'll know, right? When you integrate x squared, what do you get?
2x.
What's that? Integrate.
Oh, yeah, sorry.
1/3. You get 1/3
You
x
get
cubed.
1/3 x cubed. Yep. So that's part of it. Also, one more thing attached to this lens that I think is beautiful to think about is if you know, like you see in movies, like some sci-fi movies, people start like traveling near the speed of light, and there's this pancake effect where everything gets squashed in, right? Okay. What do we think? Is that accurate to what would be in reality, what those people would experience? Would they feel like they've been pancaked? I mean, they might feel the acceleration, but like would they feel like their nose was dang near touching the back of their head?
Yeah.
We got a yes. Anybody else?
I would say no.
Why no?
Because I'm like thinking of it as you are the constant in this situation, and if you're blowing it up to massive scales, you yourself isn't going to change.
Yeah. So I call this relative size and comparison, right? So in truth, there's no such thing as true size. It's all, we measure everything relatively, right? So if the entire universe scaled down by a factor of 1/2 from east to west, I don't know, whatever, right? In one cardinal direction, we just scaled everything down by a half and somehow got the atoms to still work and all that stuff. All the rulers would scale down as well by 1/2. Everything you're used to comparing yourself with, your depth, right? You would look over at the next person and they've also been foreshortened. So I would argue there's actually no way to detect scale differences when it comes to scaling by a factor of 1/2. It's the same with quadratics. That's one of the beautiful things about quadratics. It's why they're so heavily studied in calculus, is because they're functions that are basically both have measures of distance in either direction. What happens when you plug in, I don't know, like a function like e to the x? Can I take e of 1 meter? Does anybody know?
No, you get a unitless thing that means something else.
Yeah. So actually to use functions like e in sine and cosine, you need to ensure that the input is dimensionless, and then the output is the thing you tack a unit onto. That separates them from polynomials. Not all e to the x's are created equal. You cannot scale the range and domain and make them all look alike. They're fundamentally different curves. But with polynomials, because you plug in a unit and you get out a unit, they are limited to this scaling argument that I've made. They must all be the exact same curve geometrically. Not the same with E, not the same with sine. This is part of the reason why quadratics are so important to calculus, and just polynomials in general. So that's kind of a strong argument. Does anybody have any counterpoints or things that they feel don't hold up specifically to the constant that we found and the fact that it is a constant?
I'm just having a feel like the 1/3 that we got it makes sense in terms of the algebra and the geometry, seeing the picture, but the 1/3 in terms of the relative, wouldn't it be like a dotted line somewhere or something like that? I'm not seeing.
What dotted line in what way?
Well, because like I've seen it before, like you were talking about exponentials. Sometimes when you take like exponential, divide it by another like e to the x, you'll get like a dotted line, and it's
Huh.
like
An asymptote or something like that?
yeah. So it's like as you go further down the centimeters, eventually, like if it was like time, they both like approach like a thing. But, like
Sure.
I'm just not seeing where the 1/3 half itself, I guess.
Where the 1/3 here?
Oh wait, is that kind of like the slope sort of? I get it.
I mean,
Oh,
kind
it's
of.
area.
It's the area, but I kind of just went to exponentials to describe why the polynomials were special. Now I want to point out that Kane, you're probably thinking of something a little bit more advanced than where we're at, which is the idea that notice that I'm only using monomials. Like I'm not arguing that this is true for x squared plus 2x plus 3. I'm just arguing that it's true for x squared. Does that help?
Yeah, I think when you said area, then it made more sense. Because I'm just used to just slopes. So it's seeing like 1/3. Ramsey corrected me on the integral part. That helped too.
Yeah.
So
So yeah, it's that area under the curve that we're really looking for. And it is 1/3, and that lines up with what we thought, right? If a triangle's 1/2 quadratic, that looks like it could be a third, right? Once you buy that it's a constant, then it's not too bad.
Okay, so I have a question.
Go ahead.
So if you had a graph of like x to the sixth power,
Yeah,
then you could probably confidently say that the constant would be 1/7.
we're starting to see a pattern, right? We're
Yeah.
definitely starting to see a pattern. So, yep. We're not, I don't think I'll ever want us to do the x to the sixth volume tank, but I think like yes, the patterns and tools that we're seeing arise from here definitely apply there. It's really interesting. It does end up being the harmonic series, right? So you get 1/2 for triangle, 1/3 for rectangle or for quadratic, 1/4 for cubic, 1/5 for quartic. And that's where those integration, the accumulation constants come from in integration. So we still haven't really parsed out the change into its constituent pieces. We've just said, hey, we know that the accumulation constant exists. It's 1/3. And we know that the air, as you shrink delta H down, shrinks enough to where we can still use a rectangular approximation for small delta H. One other thing to notice that's just super surprising and is actually just more evidence that polynomials, like a monomial x squared, 2x squared, x over 2 squared, they're all the same graph if you zoom in domain and range. And an argument for that as well is notice that we didn't know a global constant. Okay, this is global. This constant tells us for any volume, give me the height, and I can calculate exactly what that height is, right? So we've got a relationship between the two. But the argumentation we went through shrunk it down to a point on the graph, right? As delta H got very small. What this tells us about polynomials is that local information sets the global tendency. So, in other words, if you know what's going on at a single point on a polynomial, you know what's going on in the whole thing. As long as you know every piece of information there is to know about that point. And that's kind of what we're gonna hop into next a little bit. But I think first is important that we start parsing this stuff out. There's two ways to do it.
I have a
And
question.
go ahead.
So this shape that we have right here, so like if you set this down, like let's say it was huge, it was like a huge tub, it went all the way up, like it was like a building. If you got really, really far from it, would it look like a triangle?
Oh, that's a good question. So, in other words, from the side, if you went far enough away, would it look like a triangle?
Yeah, or would it look more, would it the appearance tend more towards the curvature, or would it tend more towards the triangle?
I would argue that from a distance, it won't change the shape that it looks like, but there is at some point where your brain can't really differentiate because it's so dang far away. Your brain might fill in the blanks and kind of make it look more like a triangle. But I think the point of zooming in, right? When we zoom in far enough, so in other words, if I walk really close to this curved tub, at that point it will look like a straight line. That's that linear behavior that we're really honing in on. So I would say going away, I don't think it would look more like a triangle until you got so far you could hardly tell what it is at all. But if you go far enough in, the curvature starts to look straight. So at this point, there's two ways to go about it. I'm going to let you guys decide. Do you want to figure out how the triangular wedge and the quadratic wedge and the rectangular are partitioned via algebra first, or would you prefer to do it via geometry?
I vote geometry.
All right. What is
Me
it they
too.
say? You've chosen the path of pain. No, it's good. We should do it either way. But all right, so get rid of this. Well, it was useful. We already know delta V 0, so we're really going for the other two. So we've got delta V, oops, equals, what was it? It was length times width over h squared times h initial squared delta h. Okay, the triangle, we already started talking a little bit about methods that you could use to do that. What I'm going to do here, though, is we need to find that tangent line. Because what Ramsey's and Jonathan's triangle did earlier, that used a true delta W. We don't want a true delta W for this triangle. We want the delta W that's set by the linear curve. I'd call it like a delta W1. Okay, so how we find that is first we have to find the derivative of this. So kind of using similar methods. So if we find the change in width, that's going to be width over height squared times h final squared minus h initial squared. This is very similar to what we had earlier. It factors using difference of squares into h final plus h initial times delta h. But then we want to do the limit argument. Delta h approaches 0, right? We want to see what's the slope of that graph at that point. We're squeezing 2 points into one. So we can say h final is roughly equal to h initial. And we'll just call it h because now it's basically a point. And what we get there is that delta W, or I should say dW now that we're in the differential scale, is equal to, h final plus h initial is now just h plus h, that's 2h. So we get 2 width over height squared times h times delta h, dh, because we're at the very small scale now. And then this is where the tangent comes in, and this is where calculus spends a lot of its time. And honestly, Ramsey, we talked about linearization the other day. This is a good example of linearization. So this should shed some context on that. So what this tells us is that at some point, at some height h, the tangent line slope, like this, is equal to 2 times absolute width over absolute height squared times h. So if we know the slope of our linearization, right? Linearization because the true delta W comes to here. The delta W linear only goes to there. So this is a linearization. It's a linear approximation of the true change in width. We could call this the slope. Then all we have to do to find a larger delta W, or I'll call it delta W1, the delta W we gained from the linear increase, it's going to be equal to change in width over change in height on an infinitesimal scale. So we've got our slope information, and then we simply times it by how much we changed our height. This is a linearization. You could kind of think of, dH and delta H cancel, and it leaves you with dW and delta W. Not exactly true in this case because delta W and delta H aren't tiny, right? They're a little bit wider. Does anybody have any questions on this technique of using local information at a point to find a tangent line slope and take a linear step forward? Or does this make sense? It's the worst question in tutoring. What do you think? Thumbs up, thumbs sideways, thumbs down?
Can you explain why the delta H is here one more time?
Yeah. So we know the slope information for this point. We are now going to take a step upwards of size delta H. And the question we're asking is, how much delta W do we gain from that linear slope? So really what we're doing, you'd think about it, is we're relating delta W over delta H. We are equating it to the exact slope information of that point, right? That's not a true relation. That's an approximation. It works great for small delta H. But then we just multiply the delta H over to isolate the delta W.
Let me get this straight. So you're saying if I walk in the H direction, as a result, I will also walk in the W direction and multiply by delta H.
Yes, kind of. It's just, remember, we're not truly walking the curve. Otherwise, we'd get a true delta W. We'd go all the way along the quadratic. This time, we're just taking that linear step.
So it's if the droplets of water, if it didn't have that like curved part, were like rising a little bit, that's kind of like the path they would take to.
That's exactly right. Yep. If we neglected the quadratic part, the quadratic wedge, and we raised the water level by delta H, delta W1 would be the amount to the side that the water would have traveled. Yeah. And really what this is like I said, this is just the tangent line. That's all this equation is. It's a tangent line. We have a slope and we have a step. So you could think of this as like rise over run times run equals rise, or something along those lines. All right, so now that we kind of have that set up, we can now relate to the triangle shape. Because now we know the delta W of the triangle, we know the delta H of the triangle, because that's a given. And like Ramsey said earlier, delta V1, it's a triangle, so it's a 1/2. We know that because of it's half of a rectangle. And then it would be delta W1 times delta H. I'm not writing delta W because true delta W is over here. This is just the delta W that came from the triangle bit. There's also a delta W that comes from the quadratic bit. I would call that delta W sub 2. So at this point, we can find the volume of the volume change of the triangle by taking 1/2 and then plugging in dW dH times delta H times an additional delta H that was there from the triangle. So like that. It just gives us a delta H squared. And then we actually know dW dH in terms of other things. We know it in terms of absolute width, absolute height, and the height you're at. So we can plug it in additionally and say 1/2 2W. Oh my goodness, the Wacom is glitching out. For some reason, whenever I have sessions over an hour, it just starts to hate me. All right, so that's what we've got for delta V1. This is the triangle area. Notice the 2's cancel, and you're left. Oh, whoops! What did we forget for volume?
Length.
Yeah, I told you I did it too. I do it all the time. All right, put in the length there. And then we have just length times width over h squared. Oops. times h times delta h squared. Okay, so that's our triangle. And then we already had our rectangle up here. By the way, I'm going to have to start writing slower because of the way it's glitching out. So if you have anything you want to shout out while I'm being slow, please do. So that's our triangle volume. That's our rectangle volume. All that's left is to figure out the quadratic volume. And I think Jonathan mentioned something earlier about maybe subtracting one from the other. Maybe it was Kane. I think I maybe stand a little corrected here in the sense that it might be more traditional at this point to use what we know our true delta V is and subtract delta V0 and delta V1 and then say, hey, whatever's left over, the remainder has to be the volume of the quadratic bit. But there's also kind of a fun thing that I'm just going to throw out here as a guess with some justification. I'm going to guess that delta V2 is 1/3 length times width over height squared times delta H3. Okay. The reason why I guess this is because we've just described that all quadratics are the same beast, right? So it makes sense that the accumulation constant would be the same. We've also noticed that it seems like the constant cross-section terms always have delta H. The triangular terms always have delta H squared. So it stands to reason that the quadratic would have a delta H cubed. And I want you to notice that this looks almost identical to this. Because guess what? Once we've cut away the rectangular and triangular bits, what's left is a quadratic. So this is one of the interesting things about polynomial calculus is that by the time you've cut away all the lower order terms, what you're left with is a shape that is highly related to the shape of the vessel itself. So with the triangular tank, we cut out the rectangular part, and what was left? Triangular bit. With the quadratic tank, we cut out the rectangular bit, the triangular bit. What's left? Quadratic bit. But I think it would be good to pop over here and show it with algebra. And then honestly, we're probably gonna wrap it up for now and talk a little bit more because I think this is a fair bit to chew on. It's only half of what I have written in my notes, but I would rather take our time than try to just cram through this stuff. All right, so, oh, whoops, I probably shouldn't have erased that. I think it'll be fine. Okay. This is like the worst time to have a Wacom board glitching out because this is the most algebra that's happened so far. So you got the 1/3 constant length times width over h squared. Honestly, does anybody else have a tablet? They could just, Jonathan was already annotating. Could somebody save me here and just do the algebra for me? Remember, the key is wherever there's a h final, we're just going to put an h initial plus delta h.
Dang it. Right. Sees it.
You know what we should start doing is have like a 5-minute recess in the middle of the sessions, and then the Wacom might reset or something. So wherever there's an h final, we're just plugging in an h initial plus delta h. That's all we're doing. Oh, and we do just want this to be a delta h, that h final minus h initial. All right, let's factor it out. Save me as many steps as you can. Or foil it, I guess. All right, this first one, give it to me as simple as you can.
hi squared plus 2hi delta h plus delta squared h.
Yeah. And then for this next one,
hi
hi.
squared. Sorry, Jonathan. Hi squared plus delta h times hi.
yeah. And then the last one's just a plus hi squared, and then we've got this delta h that we could distribute in. All right, so when I distribute and I cancel, is there anything that cancels or combines?
Looks like there's three hi squareds,
Yeah,
and there's gonna be three hi times delta h,
yeah,
and then there's gonna be and they're all obviously multiplied by delta h as well at the end.
right. I think I may have did I goof up something here? No, there should be a delta H squared term in there, right?
Oh yeah, there is one right there.
Yeah. Okay, we got a delta
Tiny.
H squared term, and then we still have that delta H hanging out on the outside. So we're going to distribute that in because we want to separate these terms out, and we're going to see that algebra is actually doing the geometry for us, which is not always the case. All right, so you've got the 1/3 is going to cancel with the 3 for these first two terms, right? So we're going to get a L W over H squared, and then we're going to get an H initial squared times delta H for the first term. For the second term, we're going to get an L W over H squared times H initial delta H squared. And then for the last term, we're just going to get a 1/3 length times width over absolute height times delta H cubed. All right. What does this look like?
A rectangle.
Looks like the rectangle. All right, what about this one?
Triangle.
That is the triangle. There we go. And then the last one. That's whatever's left over. It's the quadratic. Okay. So notice something really interesting. The rectangular portion scales with height initial squared, right? That makes sense because if your height initial is really small, you got a really skinny rectangle. If your height initial is really big, you've got a really wide rectangle. But it only scales linearly with delta H. So in other words, because the height initial sets the constant cross section, the delta H just becomes a multiplier, just straight up and down, right? The initial height sets the column width. Okay. For the triangle, it scales linearly with height initial. In other words, a tangent triangle down here, the tangent triangles do get bigger, right? They do get wider, and it happens to be at a linear rate. So the triangles do scale this time, unlike with the triangular tank where they were the same. Okay. And they vary with delta H squared because they're related to delta W and delta H. And then the last one, the most interesting one really, is the quadratic. Does it care what height initial is?
Appears not.
It appears not, and that's shocking to us because in the triangular case, it was really easy to see like, well, of course all the triangles are going to be the same size, right? If you have the same delta H, of course triangles are going to be the same size because the tank is triangular, right? But with the quadratic, it's kind of shocking because if you think about what a quadratic might look like here, it feels like it should be different than what a quadratic looks like up here, right? It's definitely not the same shape. It's the same volume, but it's no longer the same shape like it was with the triangle. But the algebra is telling us it's the same volume and it's only dependent on the width of the section you take. So there's just some interesting things to notice. Once we get to second differences, we're going to be super happy that those are the same. Just like we were with the triangles with the second differences. Oh, great, the triangles are gone. Now this time we're going to go second difference. Oh, the quadratic wedges disappear, right? We're going to see that reduction of order continue. Now, let's see here. I think there is at least another full lesson worth of this tank stuff. I never thought it would take so long, but it is really, I think, a good way of understanding what's under the hood when it comes to calculus. Because oftentimes in calculus, we just learn the rules, we don't know where they come from, and you can still use a tool you don't know how to build, right? We've talked about that. It's perfectly valid. But if you want to do new things with the tool, if you want to adapt the tool, change how it's used a little bit, it's nice to know the inner workings. And I feel like in STEM, calculus is probably one of the most important things to really know what's going on under the hood. I would say calculus is our translation of God's language of the universe, right? I'm not saying it is God's language. I don't think the universe runs on calculus, but I think when we translate what the universe runs on into our language, that language is calculus. And so if you want to dive deep into how things change, how they interact, how they're affecting each other physically, I think calculus is a good tool.